For today's lesson, we will be discussing about the related rates and rate of change. So we will be answering some word problems that is the application of derivatives, which is again what we call as the related rates and the rate of change. So when we do differentiation with respect to time, so this is one thing that we have to remember. Suppose a certain variable x is changing at a given time t. So the expression dx over dt is called the time rate or rate of change with respect to time. So let's say again, this variable x is changing at a specific time. So we will write this expression dx over dt, or this is the rate of change in x with respect to time. Note that a time rate can either be positive if the rate is increasing or negative if it is decreasing. So it depends now on the variable that is involved here, but again, if the value is increasing, then it should be positive, and if it's decreasing, then it's negative. So here are just some of the steps that we have to follow whenever we solve problems on related rates. First is we represent the quantities that change with respect to time and other important quantities as variables. So you have to identify first what are the variables that are involved in the said problem, and you represent those quantities that change with respect to time. After that, identify the known quantities including their time rates. It's also important that you know what is the missing quantity. So you should also know that one. So next is we write an equation that relates the quantities. So once you already identify the quantities from the problem, so we have to know what formula or what equation can we use that is related with the things that we know. So sometimes we use the formula for finding area, volume, something like that. So those are the things that we can consider. Next is to differentiate both sides of the equation with respect to time. So since we will be differentiating the equation with respect to time, so we will be using d over dt. And since it involves, or our equation involves different variables, we will be applying the concept of implicit differentiation. And after that, you solve the unknown time rate. So let's have this example. The radius of a circle is increasing at a rate of 2 cm per second. How fast is the area changing when the radius is 8 cm? Okay, so what we have here is a circle. And as what we know, the radius is increasing. So the radius is increasing at a rate of 2 cm per second. Now, what we want to know is how fast is the area changing when the radius is 8 cm, because as the radius of the circle increases, our area changes as well. So these two values are just related with one another. So let's write first the variables that we have. So first is the radius, so that is r, and we have the area, which is a. Now, from the problem, we know that the radius of the circle is increasing at a rate of 2 cm per second. So that means that is the rate of change in the radius with respect to time. So that is our dr over dt, which is 2 cm per second. Next, we also know that the radius is 8 cm. So let's write r is equal to 8 cm. And then we want to know what is the missing rate, and that is the rate of change in the area with respect to time. So the missing quantity here is dA over dt, or the rate of change in A with respect to the time. Or we are now solving for the rate of change in the area of the circle with respect to time. Okay, so that's what we want to identify. Now that you already have the values, next thing that you have to do is to write the equation. Since what we have here is a circle, and we have the radius, we have the area, so what formula should we use? Again, we're talking about circle, we're talking about area and radius, therefore we can use the formula for the area of the circle, which is A equals pi r squared. Okay, so this is now the equation that we will use. And from here, we will be getting the derivative of this equation with respect to time. So, d over dt of a, d over dt of pi r squared. So you get now the derivatives with respect to time. And since we have different variables, we have a, we have r, we have to use implicit differentiation. So this, the derivative of a is 1, but since it is a different variable from t, so we have to add dA over dt. Or simply, it's just dA over dt. Again, what we applied here is implicit differentiation. Equals, and then this one, we have the pi r squared. So if you get the derivative of that, that is 2 pi r. And since the variable that we use is r, so we have to put dr over dt. So whatever variable that you use, that is the one that you will put beside d in the numerator. Okay? So that is how you apply the implicit differentiation here. Next, so again, what we want to do is to solve for the dA over dt. And looking at this one, after getting the derivatives, we already have the dA over dt, and that is equal to 2 pi r dr over dt. Now, to get the value of dA over dt, we have to solve for this one. Okay? So how are we going to solve for this? So we have 2, we have pi, we have r, which is 8, so we can just simply substitute it. We have the dr over dt, which is 2. So after you get the derivative, the next thing that you have to do is to substitute the known values or variables that we have. So 2 pi, then r is 8, and then dr over dt is 2. And then all you have to do is just to simplify that. So therefore, dA over dt is 32 pi. So 32 pi now is the rate of change in the area with respect to time. So the area of the circle is changing at a rate of 32 pi, and then the unit is cm, and then second, 32 pi cm squared per second. Now, why do we have to use squared? Because we're talking about area. Okay, so there. So this is our final answer. So the area of the circle is changing at a rate of 32 pi square centimeter per seconds. So next, let's have another example. A 25 feet ladder leans against a vertical wall with a height of 24 feet. If the top of the ladder is sliding down at 2.5 feet per second, how fast is the foot of the ladder moving away from the wall? So in problems like this, it's better if we will illustrate. So imagine that there is a wall. So there's a wall. And then a ladder is leaning against that wall. So let's just draw a ladder. And the length of the ladder is 25 feet. And the wall is 24 feet. Okay? And of course, you have the base here. So the top of the ladder is sliding down at 2.5 feet per second. So imagine the ladder is leaning against the wall, and the top of the ladder is sliding down on the wall. So what happens there is that as the ladder slides down on the wall, the height of the wall that is being covered by the ladder decreases as well. Okay? So it means as the ladder moves, there is a change with the height that is covered by the wall. There is a change in the height of the wall that is covered by the ladder. So it means that this rate of change, which is 2.5, is happening at this part or at the wall. Okay? So in order for us to represent that rate of change, of course, we need to represent the sides as variables. So we can set this as x, then we can set this as our y. So again, this 2.5 feet is the rate of change, and the height of the wall as our ladder slides down. Okay, because again, if the ladder is here, let's say the ladder is on this position, so you can see that the height of the wall that is covered by the ladder is smaller. It decreases. And if the ladder is already here, again, it decreases. So that is now the rate of change in the wall, or dx, with respect to time. Now, this is 2.5, but remember, like what I've said a while ago, if the rate is decreasing, so it should be negative. And as what we notice here, as the ladder slides down, the height that is covered by the ladder decreases. Okay, so it should be negative 2.5. So negative 2.5 is our dx over dt, or this is the rate of change in the height of the ladder, in the height of the wall, with respect to time. Now, the question is, how fast is the foot of the ladder moving away from the wall? So, of course, if the ladder slides down in this manner, of course, the feet will adjust as well. So, it will move away from the wall. So, what happens is that there's also a rate, or there's also a change in our y. So, that is what we want to identify. So that is dy over dt. So that is the one that is missing. Now, why not the wall? Because the wall will not change in its length. It's still 25 feet. As it glides, so it will maintain its length. The one that is changing here is the height of the wall covered by the ladder, as well as the base. So that's why we are looking for the dy over dt. Now, we already know the missing quantities. We have to write now the equation. So what equation now should we use? So if you will look at this graph, or if you look at this illustration, you will see that we formed here a right triangle. So this is actually a right triangle. Therefore, we can use the Fetagoria Theorem, which is the sum of the square of the legs equals the square of the hypotenuse, which is, in this case, is 25. So 25 squared. So this is the equation that we will be using. So let's just write x squared plus y squared equals 625. And now let's get the derivative of each with respect to time. And then y squared equals d over dt 625. Okay. So next, let's get the derivative. So first is this one, the x squared. So its derivative is 2x, but then again, this is x variable, and we are getting its derivative with respect to t, or with respect to time. That means we will be adding here dx over dt. Okay? Plus, and then this one is 2y. Again, it's a different variable, so that will be dy over dt. And then last, get the derivative of this. This is just 0. Okay? So you have 2x dx over dt plus 2y dy over dt equals to 0. Again, what we want to identify is the dy over dt. That means we have to isolate the term with the dy over dt on one side. So we will be moving this one. So we have the 2y dy over dt equals negative 2x dx over dt. Since we want the dy over dt, so let's just divide both sides by 2y. Cancelled. So you have now dy over dt equals, then this is negative x over y, and then dx over dt. So this is now the equation that we will be working on. Okay? Now, the next thing that we have to do is to solve for the value of dy over dt, which is equal to negative x over y times dx over dt. So, we need to substitute all of the values that we have. So, if we will just go back here, we have the x, which is 24. So, that's the value of x. So, let's write here x is equal to 24. What else do we have? We have the dx over dt, which is negative 2.5. So that is negative 2.5. But we don't have the y. We don't have the y variable. But remember, this is a right triangle. Therefore, we can apply the concept of Pythagorean theorem. So, what we will do is, let's use the Pythagorean theorem and solve for the value of y. So, x squared, so that's 24 squared, plus y squared equals 625. Let's just solve for y. So, this is 576 plus y squared equals 625. Then y squared equals 625 minus 576. So we have y squared is equal to 49, or y is equal to 7. So that is the value of y. So we already have complete values. So we can now substitute. dy over dt is equal to x. So negative x is 24 over y, which is 7, times the value of dx over dt, which is negative 2.5. So if you simplify that one, so we will get an approximate value of 8.57. So this is now our rate of change with respect to t. So we will write here the foot of the ladder of the ladder is moving away from the wall at a rate of approximately 8.57 and then feet per second. Okay, so that is our final answer. So let's have another problem. Jessie is flying a kite at a height of 120 feet, which is moving away horizontally parallel to the ground at a rate of 9 feet per second. If 130 feet of string are already out, at what rate is the string being released? Okay, so let's draw the problem. So let's say this is Jessie. And she is flying a kite. So let's say it's like that. And then let's draw the kite at a height of 120 feet. So the height is 120 feet, which is moving away parallel to the ground. So the movement of the kite is horizontal, so it is not increasing in height anymore. So the movement is horizontal to the ground at the rate of 9 feet per second. So if this is the ground, so that means it moves parallel to the ground at 9 feet per second. So as you can see here, we formed again a right triangle. And this is, we can set this as our x, and then this is our y. So this 9 feet per second is for the rate of change of x, because it represents the movement of the kite parallel to the ground. So we have dx over dt, which is equal to 9. So if 130 feet of the string is already out, so this one is 130. At what rate is the string being released? So of course, if the kite is moving, the string also increases in value or in length. So this is what we want to identify. How is the string changes in length as well? Since this is our x, this is our y, we can set this as another variable. Let's say this is z. Therefore, we are looking for the rate of change in z with respect to t. Again, that refers to the rate of change in the string with respect to the time. So that is what we want to identify. Now that we already know which one we want to identify, let's write now the equation. And since this is another right triangle, that means we will be using again our Fetagoria Theorem. Okay? But this time, what we will do is we will be just writing here x squared plus y squared. So we know it's not moving, it's constant, so we'll just set it as 120. And then for z, since this is moving, so let's just write here z squared. And then let's get the derivative with respect to t of 120, also this one. So this is 2x dx over dt plus, this is 0, and then this one is 2z dz over dt. Okay, and then again what we want to solve is the dz over dt. So since it's already isolated, so we can just simplify this. So let me just change this to 2z dz over dt equals 2x dx over dt. And then let's divide both sides by 2z so that we can just have the dz over dt here. So cancel. So we have dz over dt is equal to x over z times dx over dt. So it's just the same as our last example a while ago. So after this one, we have to substitute all of the values that we have. So we have the value for z, which is 130. We know the dx over dt, which is 9, but we don't have the x. So we still need to solve for that. So let's use the Fetagoria Theorem. So let's use this formula again. X squared plus 120. Oh, by the way, this one is squared. Anyways, still be equal to 0. So we have here 120 squared equals z squared. So x squared plus 120 squared is 14,400 equals z. Our z is 130. So square of 130, that is 16,900. And then x squared equals 16,900 minus 14,400. And that will give us x squared equals 2,500, which is equal to 50. So that is the value of x. And now let's substitute the values here. dz over dt equals x is 50 over z, which is 130, times the dx over dt, which is 9. So therefore, what we have here is 45 over 13, or approximately 3.46. Okay, so that is the rate of change in the string. So that is the rate of how the string is being released with respect to time. So the string is being released at a rate of approximately 3.46 feet per seconds. Okay, so that is our final answer. So that's it for today. I hope you learned something about how to solve problems involving related rates, and see you next time.